Today we had to discuss LS coupling and JJ coupling. Before we go to LS coupling and JJ coupling, some basic definitions are there which we should understand. Many of them you already know actually, just to rewind them. For example, we will use some terminology hereafter. Some terminology will be used hereafter. We have already used them actually, but it will be used the most often in the coming topics. For example, one of them is status. It is a state of an atom. State. So we say that an atom has a ground state. What does that mean? A ground state. How we define that state? What actually state is? Or what excited state, in an excited state, what does that state mean? Simply, state of an atom, it determines actually the state. That means I can write them motion of all electrons of an atom. And is determined by and is specified by. So how we represent a state are represented by. How can we represent the state of an atom? By listing 4 quantum numbers. By listing 4 quantum numbers, okay? So that means state of an atom is actually the state of all those electrons, all the electrons, or generally these electrons are termed to be the valence electrons actually. And these states are specified, or they are represented by listing their quantum numbers. That means by representing the quantum numbers of an electron at a particular energy level, at a particular state. And the lowest energy state is called as ground state. That is another topic, that for what value of a given quantum number the state is the lowest energy state. For example, L. So for what value of L of a given atom, it is the lowest energy state. And when it will be a higher energy state, then at that time what will be the value of L? Will it be more? Will it be less? That we will discuss in the next. And also, if for example, if different quantum number of electrons, electrons of different quantum numbers have same energy, that means if several states have same energy, then they are said to be degenerate. Same energy states are called as degenerate states. Degenerate states. So when their energies are same of different states, then the energies are same. For example, 2s2, when we are not incorporating any spin, that ms quantum number. So 2s2 has 2 electrons. 2 electrons are in 2 different states, but they are of same energies in s. So they are degenerate with respect to the ms. So degeneracy is not removed in case of the spin. Similarly, you have 2p2. Then another concept is, which is energy level. Energy level. And energy level is formed. When different states having same energies, they combine. That means collection of states having same energy. Collection of states having same energy. But remember that the same energy is calculated in the absence of any external factor like external magnetic field, external electric field. So whatever there is internally present in the atom, whatever the sources of energies, sources of perturbations, sources of interactions, they are present in the atom, they will be treated as a ground states. Actually they are not excited states. So after all those interactions, perturbations, and in this energies, internal energies, there's a one state actually corresponding to a given atom. So there's different states. When they have same energies, they form an energy level. And we characterize energy level energy levels are characterized by quantum number J. They are characterized by the quantum number J. And with lowest level, lowest energy, ground level, ground state level. They are ground level, sorry. So that's called as ground level when we have a lowest energy state. For example, J equal to 3 by 2. What does it mean? You can have different possible combinations of this. So L equal to 1, S equal to 1 by 2. That is 1 plus 1 by 2 is 3 by 2. Okay. You can have different combinations. Yes. So when you have such type of energy states, for example, L is equal to 0, S is equal to 3 by 2. In that case, this is not, is it possible? No. So in this case, for this is one state. Similarly, when you have J equal to 5 by 2, so you can have different combinations of L and S to get J equal to 5 by 2. Like S is equal to 1, L is equal to 3 by 2. S is equal to 0, L is equal to 5 by 2. Sometimes this is also possible. So when this type of states, when there are same values of J for a given J, the energy levels are actually degenerate. They have same energies. But in absence of any external energy, when you apply some external perturbation, the value changes. We have another concept that is called sublevel. Sublevel means, for example, you have one energy level, 2p, and you apply some external field, it goes 2p, 2p 3 by 2 here. It goes 2p, yes, 2p half 3 by 3 by 2, yes, and this is it. So it is separated, but in external field. When we apply some external field, there may be the spin splitting as well. When you apply external field, the spins will be up and down. So they form sublevels at that time. That means an external field will split an energy level into several sublevels. Each will be characterized by one or more magnetic quantum numbers. So each sublevel will have different quantum number. The term is an important. We will use this actually again. And term is determined by collection of those levels. Collection of those levels which are characterized by orbital angular momentum and multiplicity. That is, multiplicity means that multiplicity, how many possible combinations. Multiplicity means how many possible combinations of spin actually. possible combinations. For example, if your S is 3 by 2, okay, then your MS will be, what will be it? It will be 2S plus 1 values. So multiplicity MS is actually the possible combinations of this S corresponding to a particular spin moment. Total spin actually. This S is total spin of many electrons. And if you see here, MS can have 2 into 3 by 2 plus 1 values. That is 4. Okay, that goes like this. It is simply becomes 3 by 2, 1 by 2, minus 3 by 2, minus 1 by 2. Okay, and this is a possible combinations of this spin, and this is called a multiplicity. So term will be actually determined by, it is also called as a spectroscopic term. Spectroscopic term. For example, it is represented as L, total L. It is a total actually, what the resultant L will be. From, if you have 2 electrons in combination, so L will be for 2 those, and what will be the final L for different combinations? It is here 2S plus 1, and it is J here. So it is L, J, 2S plus 1. So this representation is called as a spectroscopic term, and it is characterized by this orbital angular momentum, this multiplicity, and then J. So changing different J values will result in different spectroscopic terms. 2S plus 1 will be constant, L will be constant, and it can change sometimes when there are more number of electrons. So in this way we will study in detail this. This will be detailed maybe in the next class, or even if we touch it today. Then electronic configuration, you know that configuration is you assign an N and L quantum numbers for the orbitals of all electrons, and this is called electronic configuration, where you assign the quantum numbers N and L to all electrons of the orbit, all the orbits of, or all the electrons of an orbit, and then it is called, this process is called as electronic configuration. Then there is definition that is called equivalent orbit. Equivalent orbitals. Those orbits or orbitals having same N and L. Those orbitals or orbitals having same N and L, those are called as equivalent orbitals. And the electrons which are present in these same N and L, they are called equivalent electrons. For example, I will give an example. Like (3p2). So here for these 2 electrons, your N is 3, your L is 1. These 2 electrons, these are called as equivalent electrons. Others, like we have non-equivalent. Non-equivalent means 4s 3d. These are non-equivalent electrons. So equivalent are where we have same N and same L. Like we have 45. So these electrons have same N, same L. So these type of electrons are called as equivalent electrons.
सर इसमें 2 क्या रिप्रेजेंट करता है?
ये नंबर ऑफ इलेक्ट्रॉन्स है. आप कॉन्फ़िगरेशन कैसे करते हो? 1s2, 2s2.
Yes, sir.
Okay. These are number of
Okay.
electrons. Then statistical weight of an this level of an energy level. This is actually the number of distinct states number of distinct states, how many states in a given energy level are, and that is given by in a specified, I will write here, collection of levels. This is called state. It is given by 2j plus 1. So it is called as 2j. It is given by 2j plus 1. And this is for an energy level. If you have a term level, energy term, it is then given by 2s plus 1 into 2l plus 1. Statistical weight. And these are how many different states there are in a given energy level, that is 2j plus 1. And if you want to find the statistical weight of a term, then it is given by 2s plus 1, 2l plus 1. For example, if you have one electron, this one electron will have s equal to half, l equal to 0. And in this case, if you take this, so it is 1. It is 2, sorry. It is 1 here, plus 1 is 2. This will be 0. This 2l plus 1, it is 1 into 2. So that is 2. And it is also represented for a single electron. The statistical weight is also given as 2n square. What is the quantum number actually here? Sorry, for this per single electron. Okay, so you put up the value of this n in this case here, because we are treating the n electron in a ground state in s orbit. So that's why we have taken this configuration. This is for s orbit. If you have in general the orbit, nth orbit, and sorry, you have, yes, n, okay, 2. If we take n equal to 1, yeah, it is 2 into 1 square, that's 2. So for this state, s. Then there are different components of a spectral liners. That is like component. We have already done these. We have line of a spectral series. We have multiplet. We have resonance line. This all I have already introduced here. And this is the component, means you have one energy level 2. There's a transition between these two levels. This is the component actually. And these are, since the two levels, there may be different states corresponding to different levels. So here we have different than components. So group of components can form lines, because in a different two component there can be more than one line, because of the different states, presence of different states in a given line. And there's a transition between two levels, and it will give us a line. So it's not necessary that we have a single line. We can have more than one lines because of the different number of states corresponding to that given energy levels. These we have already done, and we will see them again when we discuss those other effects like Zeeman effect and Stark effect. What our main topic today is, actually, these were some definitions. I will send you these separately. We have actually to study spin orbit, or simply the LS coupling or JJ coupling. Now, in LS coupling and JJ coupling, first we need to understand that in the case of earlier classes or up to now, what we discussed one electron atoms mainly. For example, whether it was a affine structure, we discussed it for hydrogen atom, and in hyperfine structure you can also discuss for that for hydrogen atom. We have line spectra, Bohr's theory, that all we discussed for one electron atoms. So for one electron atom, those electrons which are responsible for any type of activity in an atom. Those are called as optically active electrons. So which can take part in physical phenomena like transitions between two energy levels, like transitions for two different energy levels. So the electrons which are responsible, those are generally those which are in the outermost orbitals, which are free generally, and those are called as optically active electrons, because when you shine some light on them, you give some energy to them, they will excite, they will move from one point of energy to another point of energy, from lower state to higher state. And what about those other electrons? Actually, they are in close to the nucleus core, hence tightly bound, so they do not interact much, because the strength of the external signal, that means the energy, that corresponds to only, for example, if you have here, there are two electrons here, these two electrons are free, actually they are of very, they need very low energy to be excited as compared to electrons which are here, because these electrons will be closely bound to this, and these will be loosely bound to this nucleus, as they have a lot of space here, they are not attracted by the same amount as these are attracted. So these two electrons become actually optically active electrons, as they can be easily excited and they can easily take part in any physical phenomena like absorption, excitation, scattering, and they can have a magnetic moment which can interact with the external field. They can have an electrodipole moment which can interact with the external electric field, which is an example of Stark effect. Similarly, they can have this, they can be optically excited, and so they are called as optically active electrons. Now, in case of this one electron atom, we have only one electron, which we were talking about. So we don't have any interaction from any other electron if we have if we are treating with one electron atom. If we are treating with one electron atom, so that means we have only one electron which will be responsible for any physical phenomena or physical property of a given atom. And there is only one interaction, that is Coulomb interaction between nucleus and electron. That is one part. But what about if we have more than one electron? If we have more than one electron. So in that case, when we have more than one electron, it becomes many body problem. Like helium, lithium, or any atom with Z greater than 2, Z greater than 1, atomic number greater than 1. So we have then many optically active electrons. Not only one, but we have many optically active electrons. That means several optically active electrons. Okay. In that case, we have to take different interactions, because there are more than one electron now. There is more than one electron, and if this is a nucleus, these are the different. So you have electrons here, for example. So in an atom, these are not in the definite paths actually. This was just a representation, but in practice they are not just like in a fixed orbit, but they can move anywhere in this space, in this region. It's a probability that they can be anywhere. So when they continuously move in a given region of space, they can have different types of energies and interactions between them. I will mention some of them. For example, when we consider an atom of Z atomic number, Z electrons, and they have nuclear charge of Ze and N electrons, then we will study this system by considering number one is that we have kinetic energy of electrons, all the electrons, and their potential energies in electrostatic Coulomb attraction or attractive field of the nucleus. Okay, and this is one. The second point is that they may have the electrostatic Coulomb repulsion between the electrons. One is that between the electron and the nucleus, positive and negative. Another is electron and electron. This is also sometimes called as residual interaction. Residual Coulomb interaction. Electrostatic interaction energy. This interaction energy. Okay. Then there are another interactions, like there is spin-spin correlation energy. Like for example, spin-spin correlation means if you have parallel spins, what will be they do? They will repel each other. If you have anti-parallel spins, they will be attracted to each other. They will be closely spaced. These will be spaced far away. This is magnetic in origin. That means spin-spin magnetic moments. The four is that we have spin orbit interaction. Magnetic interaction energy of electrons. So these are the main contributions to the various interactions energies of an electron in an atom, or of energy of an atom in whole. And besides these four different contributions, and remember that energy, total energy, we write it in terms of Hamiltonian, and the various terms which will be included in a Hamiltonian, that will be that kinetic energy term, which is I equal to 1 to n p square by 2m. Pi is the momentum of the ith electron, so it will be I, mass m. And then we have another term which is I equal to 1 to n, and this is negative. Actually it is an attractive potential, nucleus and electron, which we have I electrons, so their position vectors with respect to the nucleus will be I, so ith electron. And then there's a mutual electrostatic energy, that is between electron and electron, and that is, I can write summation I equal to 1 to summation of I equal to 1, j is equal to I equal to m minus 1. I can write in this way, and this is an attractive potential, repulsive potential, sorry, and it is E square by Rij. This will be represented, and where Ij is actually the distance between the ith and the jth electron, because this is a mutual interaction. This can be also written as summation I is less than j equal to 1 to m, because if I is 2, I is less than j. So if I is 1, j will be 2. So it is first electron, it is second electron. So similarly, if I is 2, j will be third electron. So this is how I is less than j equal to 1 to n. Now, so these are the different actually terms which will be represented in terms of an Hamiltonian for representing the total energy of the atom. But besides these terms or besides these contributions, I will remind you that there are some other contributions, like we have relativistic, which we did actually, correction. We have other, that is electromagnetic actually interactions between the atoms and the electrons, this nucleus and electron. That's just we have Lamb shift, but these are very small, these interactions. Now, how to treat this atom which consists of many electrons, many optically active electrons? And we here already know that up to hydrogen single electron atom we can treat it perturbation theory by or using the Schrodinger equation. Sorry for that. Using Schrodinger equation, it can be used to determine the total energy state of an atom. But for higher number of electrons, when we have many body effects, especially in fermions, and then where there are spin interactions, mutual interactions, then we use approximate methods. And to solve this, one of the mostly used approximation is that is called central field approximation. So the name of the approximation is central field approximation. And in this central field approximation, what approximation actually we make is that each electron is treated as if it were moving independently. That means an electron moves in a spherically symmetric potential. If this is a nucleus and this whole here is somewhere electron which we are considering, and this electron will move independently. It will not be affected by any other sources near it, but it is moving independently under the influence of there is a spherically symmetric potential. This is spherically symmetric potential here, which will be experienced by this electron, nothing else. It will be only this spherically potential, symmetric potential. So there's a spherically symmetric potential, and this spherically symmetric potential is experienced by this electron here. And this spherically symmetric potential, it consists all those effects. It includes all these interactions which we have discussed above, especially this mutual interaction and this nuclear kinetic energy is there. We are not ignoring that, but these two interactions are independently combined then, and to give a resultant spherically symmetric potential here, which is experienced by any electron which we are considering. That means the Hamiltonian, which is formed by these terms, now will consist of spherical symmetric or a spherical averaged potential. That is, which will contain first, that is kinetic energy term, the potential energy between the electron and the nucleus, that is E square by R, this term, and it will also contain E square by Rij. So spherically symmetric potential is average potential of all these three actually, which will be included in this. This is the approximation or the statement of a central field approximation, and that is also called as Hartree central field approximation, and it has very practical applications actually, huge number of practical applications. So energy of then each electron which is moving, actually optically active electron which is moving there independently, it is determined by then quantum number n and l. So there are central field orbits actually there. So those orbits which we discussed actually, those now become central field orbits, and they are represented by a quantum number n and l. the total energy of the atom actually equal to then becomes total energy of the atom. It becomes actually E total is equal to constant total energy of the core. Core means except there's active electrons, optically active electrons, which are free actually, valence electrons in a rough term I can use, and plus sum of total energies of the optically active electrons. So they are the two parts of this total energy. One is this nucleus plus this extra orbital, which are core actually, and this form a spherically symmetric potential here, plus the energies of these electrons, optically electrons, optically active here. So this is core actually. Core electrons actually, they do not take part in optical excitations, any excitation, magnetic, electric, or optic. So the name has been given as optical excitations, but this includes the excitation by external electric field, magnetic field, all those, because the energies are very large here, this energy, as compared to these, which I already told you. So the energy of the core is constant. It remains almost constant because the core electrons do not take part in any optical excitation. That is how we treat the core energy as a constant. Then it becomes this energy, optically active electrons. Also, it is important to note that the energy does not depend on ms and ml. Space quantum numbers, space quantization, ml and ms, spin quantum number. So these states are degenerate, having different values of ml and ms corresponding to a given level. Those states are degenerate. So in this approximation, in central field approximation, which was developed by actually Hartree-Fock and Slater, by Slater determinant, then using the Hartree-Fock approximations, and they developed the central field approximation. They worked under this and developed a model actually, how we solve the multi-electron wave function, or how we solve the equation, Hamiltonian or the Schrodinger equation for a multi-electron atom. So these levels, these central field approximations, the levels are then, there are different number of degenerate energy levels, which are associated with each electronic configuration. When you configure those electrons, when you distribute them, some states or energy levels of those configurations remain degenerate in ml and ms. Then these degeneracies can be removed actually by external perturbations, and some of the degeneracies are also removed by internal perturbations. Internal perturbations. So internal perturbations means like spin orbit interaction, which we also did, that is fine structure. These become internal perturbations, like hyperfine structure, hyperfine interaction. These are internal perturbations. So these contribute to these perturbations also drift some of the degeneracies. If there are some degeneracies, that's also lifted in this case, like the degeneration in the L from the fine structure. Now, what this has to do with the LS coupling or the JJ coupling? The residual, this is sometimes also called as residual or mutual, or it is sometimes called as non-spherical electrostatic interaction. Electrostatic interaction. interaction, and spin correlation or interaction. These are large values, largest of other remaining interactions. That means the value of energies due to these interactions, spin and residual mutual interaction, mutual non-spherical electrostatic interactions, these have significant effect on the energies of the electrons. The value of these energies is large as compared to other contributions, which I have already told you about, different contributions. And this happens especially for those atoms which have low atomic number, Z less than 30, 20, 40. Lighter atoms, mainly for lighter ones. That means, what is this residual? How we represent this residual? We know that we have an orbit, and electron is here, electron is here, electron is here, electron is here. In a particular definite energy of orbit of energy, they have a particular probability, and this probability is that they have a definite probability in this particular region. So these electrons will have, in an orbital, due to orbital motion, they have an electrostatic interaction between each of them, or between this electron and this electron and this electron, this electron and this electron. So there is an electrostatic interaction, that is repulsion, between these, and when they have this repulsion, they can have a spin-spin interaction between them. So this electrostatic will be due to orbital angular momentum, and spin will be due to S, spin magnetic moment. This is important to understand in case of when we go to the LS coupling, because in that lighter atom, in those lighter atoms, the spin-spin interactions and the orbital, that mutual electrostatic interactions, they become significant as compared to the other kinetic energy, and as well as those nucleus and the electron, because nucleus and electron are at some particular high large distances, and nucleus is considered to be a point mass, heavy point mass, because it is large actually size as well as the heavy mass. So that is why these interactions in these lighter atoms become of a reasonable magnitude. And then to calculate the energy, we need to calculate the L of all the electrons, we need to calculate the S of all the electrons.
सर बस आज इतना ही पढ़ेंगे.
Okay, I'm finishing it up here, don't worry.
Okay, sir.
So we calculate the total angular momentum J, then it becomes L plus S. Okay, where this L is actually L1, L2, L3 up to. These are combined actually. These are different possible combinations. We will discuss them in the next lecture then. And so LS coupling becomes actually important in lighter atoms, and in those atoms, the residual, that is electrostatic mutual interaction between electrons, and the spin-spin interaction between the electrons, that becomes significant. And when this is the case, we have LS coupling. That means we combine the orbital angular momentum, we combine the spin angular momentum, then combine these two individually. After summing them, then get the total angular momentum of the atom. This is what the LS coupling how the LS coupling is done actually. In case of JJ coupling, that occurs in heavier atoms, because the number of electrons and protons become large, the size of the nucleus become large, the effect of the nucleus and the electronic potential become large. Similarly, those other interactions, like we have spin-spin and this residual, they become less as compared to those interactions. And in heavier atoms, we have then JJ coupling. JJ coupling means that you take, for one electron, if we have electron 1, you take it as L1 plus S1. For second electron, you take L2 plus S2. Then combine. This gives us J1, this gives J2. Then JJ coupling becomes total J is J1, J2, J3. This is JJ coupling. Okay, so we will discuss then LS coupling tomorrow in a separate topic.